When our group at ETH Zurich was approached by Reaxys in order to evaluate their predictive retrosynthesis tool, we wanted to go about this in a way that is as thorough as possible in order to give us the most insight into this tool. And the workflow that we developed for this together with Reaxys was that we split our research group into a couple of teams. That was 7, comprising of 3 to 4 researchers of varying academic ages, so to say. So junior PhD students, postdocs, senior PhD students. So we get a large variety of chemical know-how within the groups. We then selected 30 molecules, which you can see at the bottom here. These were partly selected by our group and partly selected by Reaxys. This is in order to get a huge variety of molecules, and I think you can see this down here. The structural diversity is quite large. You have drug-like compounds and molecules that more resemble classical natural products, like more in the diterpenoid space. This is something where our group, for example, is very interested in. We then had to sort of devise a plan to test the tool. And so first for this, we started actually creating a synthesis route for each of the molecules without using predictive retrosynthesis. This was sort of to have a benchmark in order to test the program against later on. These routes were discussed within the groups, but also then within our whole research group. And generally it was also documented how much time and effort was required in order to arrive at a route where we would think that this could be a good starting point for the lab synthesis. Next, we moved towards the predictive retrosynthesis tool. We put the molecules in the tool, compared that, got routes out, then compared those routes to our routes. And if that was the case, we used the ideas and the input from the retrosynthesis tool also going forward into other routes. And again, we measured the time and the effort that was required. Now, as the tool is a constantly updating sort of work in progress here, it still works, it already works very well, but there's constantly new features being added. We often enough rerun certain molecules, especially the ones where the program might have had troubles at the first time, in order to again assess how these new features can help in dealing with more complex problems. So to kind of see how our group judged this tool, we want to give a quick overview of a survey done within our research group regarding the predictive retrosynthesis tool. I have to preface here that this is a survey that was done quite early in our collaboration. And I think some of the answers might change a bit, although I would say mostly only to the better here. So as you can see, was rated by the group as very intuitive to use and having a very friendly user interface. I would say this generally correlates nicely to the fact that it's integrated within Reaxys, a program that we use on, I would say, more than a daily basis at this point. So if you're able to use Reaxys, using this tool comes very naturally to you. And I think this reflects within the answers given by the group. Furthermore, the possibility to review reaction conditions and literature references for those predicted steps, as we have seen with Abhinav's presentation here, was again rated quite highly by the group, again showcasing that the integration into Reaxys was really appreciated by most people within the group. a bit more of a mixed bag of answers comes to the question of, does the tool support the generation of new ideas? We see that it's still overall quite positive. However, there it was a bit more mixed. The thing why this most likely is the case, and this also came out of discussion with people in the group, is that especially for more complex molecules like natural product-like molecules, the program, especially in the beginning, struggled to a degree and often enough could not lead to a satisfying result. I would say if this, with the new features that we're also going to present later on, this again has shifted within our group towards a more positive outlook. So again, this is, I would say this is still overall a very, very good rating here. So just to see about the molecules that we want to talk to you about today. These are the 6 molecules that we have picked as an example. You can see as examples, you can see that there's again a variety that hopefully reflects the 30 molecules that you've seen on the previous slides. There are more drug-like molecules in here and also molecules that look like they could be intermediates or even natural product, intermediates in the synthesis of natural products or natural products themselves. In order, so we have a huge variety and hopefully see how the program deals with all of them. You can see the structures are mostly novel, besides one known natural product here. And for none of these, we have a reported synthesis. So without further ado, let us just go through our syntheses at this point. So the first molecule, as we see here on the left, we have a human-generated route that starts from an inexpensive starting material available on the Sigma Aldrich catalog, which is then transformed over a couple of steps into the final product. We can see that this is an approach that focuses very much on building up complexity step by step. There's a very early fragment coupling of 2 somewhat complex fragments, and then afterwards the complexity is built up step by step. We can see this is very much an approach where we can see the influence of, I would say, an academic research group. The starting materials that are chosen are inexpensive and so easily available to our research group. If we compare this to the retrosynthesis tool route, we see that the retrosynthesis tool picks a slightly different approach here and focuses on the synthesis of 2 building blocks that are then in a final step, which I kind of refer to as a sort of Pigdish-Spengler type reaction, coupled together to give the final product. We see that this is, I would say, a very, very robust approach that I would say I'd be glad to try in the lab. It also looks quite modular because, again, it brings 2 building blocks together quite late in the synthesis. However, what we can see that the program traces back to what looks like more complex starting materials. This is again because the program has different parameters to choose from here, and the parameters chosen here were for also include CROs or other companies that sell chemicals at a higher price. This is not a problem. If you want, you can prepare both these starting materials from cheaper commercial sources, but it just highlights how the approaches can be different. However, the tool gives the option for every user here. If the budget is higher, you can go to the more complex starting materials. And for researchers that want to start from less expensive starting materials, the tool also would give this option. But again, we see 2 routes that look very robust and doable in the lab here. So the second molecule is actually a molecule where probably Moritz Hansen would be the person that should talk about this the most, but he has his part of the presentation later on. This is a molecule, this is part of a molecule that I would say is very close to his heart. It is sort of a fragment of a total synthesis project that has been going on in our group by Moritz Classen and still to this date goes on. But so if you look at the synthesis of this, we can see that the human route again chooses inexpensive starting materials and then transforms them to the fragment here. We can see that the key step chosen by the group here is this Michael addition of a thiolate and then trapping of the resulting enolate with an aldehyde in order to construct 2 bonds in one step. And then after deprotection, the fragment is revealed. We can see here that this is again a very quick route. Obviously, there is a bit of risk involved in this two-step procedure, but the group seemed to be willing to take this risk. Looking at the retrosynthesis tool route, we can see that here again, with cysteine, a very inexpensive starting material was chosen again, which and then the construction is done a little bit differently. So instead of a Michael addition, a coupling leads to the thioether bond, and then amide formation closes the amide formation, and then aldol reaction leads to the final product. What we can see here, however, is that sometimes the tool might struggle with functional group tolerance here. So we can see that the amide coupling is done in 2 steps. It basically forms an acid chloride out of our acid and then Bock deprotects and forms the amide bond in 1 step. Aqueous HCl and acid chlorides are generally not the most, aren't the conditions that go that well together. So the program struggles a bit here. However, this is a problem that is easily alleviated by, for example, changing the order of steps. This showcases that the program, while it comes up with routes that are very feasible, it still needs the review of experienced chemists in order to spot these mistakes that sometimes happen and to maybe slightly adjust the route in order to make it easier to perform or possible to perform in a laboratory setting. So we now move to these sort of natural product-like examples. Again, this is a molecule that had been a previous synthesis project in our group as a fragment of a larger molecule. We see here that the human-generated route chooses an approach where a cuprate addition followed by a Konya-ene type reaction builds up the decalene core, and then reductive amination and amide formation or carbamide formation leads to the desired product. Again, I would say this is a very robust route that quickly leads to the final product here. Interestingly, the approach chosen by the retrosynthesis tool is quite comparable in the sense that it also performs a conjugate addition. However, then a condensation reaction instead of an ene reaction is chosen to construct the decalene core. This again looks very feasible. We then move on. A Wittig olefination gives the exomethylene here, and then the last steps with reductive amination and amide bond formation are the same. The one question that probably comes to mind here is we have a diketone in this molecule and have to perform a selective olefination on one of them. This is again something where the integration of the tool into the Reaxys environment comes in very helpful, because if we ask ourselves the question, is this potentially possible? We can also now, for example, copy this as a substructure to a search query and try to find out whether those kind of selective olefinations are possible. On first glance, for example, I would say this is very much a possibility. The ketone that we try to do an olefination on here seems to be the less hindered of the two. But again, the quick access to Reaxys search functions here gives us the opportunity to again review the chemistry that the tool suggests in order to find out whether it's feasible to run in a laboratory or not. So again, I would say a very nice route, and again, the integration into the Reaxys interface is of a large help here. Which brings us to probably my favorite example, because this is an example I really like to talk about a lot, because this molecule was chosen quite deliberately by our group. It is sort of a derivative of an intermediate that we have used in a previous synthesis, and we kind of put this in here on purpose, because looking at this molecule and also looking how our group prepared a very similar intermediate, this molecule really to us was a prime example of a nitrile oxide cycloaddition reaction in order to quickly construct the ring system here. And this is exactly what the group did. They moved forward, built up the cycloaddition precursor, and then as a last step, performed this cycloaddition here. So we really put in this molecule in order to kind of find out whether the program is able to find what I would say is a rather complex disconnection here in order to construct this heterocycle. Interestingly, the program didn't, and instead chose an approach that we weren't aware of at all. This oxidative cyclization of oximes on tertiary CH bonds is actually a well enough precedented reaction that this is probably a very feasible try in the lab, but we were simply not aware of this. So the program sort of removed the bias here on even a molecule where we would have said that it very much puts you into one corner of chemistry. So we are really delighted to find this, because this was really nice. However, then looking at the start of the synthesis towards the starting material, we see that now there's a lot of problems. The program here struggles a bit with the complexity and tries to move around a ketone inside a molecule that otherwise bears basically no functionality, and really comes up with a starting material route that is not feasible at all. However, as I said before, with new features being added, we revisited those kinds of molecules, and this was one of them, because a new feature that also Moritz Hansen most likely will show you later on is the possibility to design custom routes and to sort of guide the program through parts where it struggles a bit, and to take it by its hand to a degree. So what we can see down here is again only predicted steps by the tool, however with human input that sort of lead to a route that as any route might be could still have problems in and of itself, but at first glance gives the opportunity to construct this precursor, which is then again used in this disconnection here that we still think is a very, very innovative one. So again, this I would say is quite a nice showcase on one hand that the tool is able to, because it has such a huge database of reactions, to find reactions that we might not be aware of at the moment. I mean, maybe I'm outing myself here. Maybe this reaction is known to everybody else. I wasn't personally aware of this reaction beforehand. But I guess as it is with the large field of chemistry, there's always a reaction you don't know, and the tool can help us identify those reactions. And even then, if it struggles with other parts, we can then guide the tool through those steps in order to find a route where we would be comfortable enough with to try it out in a laboratory. Bringing us to the next molecule. Again, this I would say is a very nice example here. We can see, and I'm just showing the retrosynthesis tool route here at the moment. We can see that the tool constructs this again rather complex molecule through a late stage coupling reaction. We see a very nice construction of this cyclopropanol moiety here through a nucleophilic opening of an epoxide. in order to quickly construct both of our fragments here, especially the lower one. Again, we have to say, right, that the starting materials look quite complex. Let me assure you, both of these starting materials are commercially available. However, starting materials with those kind of complexity often enough, of course, carry quite a price tag. So again, it is possible to extend this route, bringing it back to cheaper starting materials if, for example, this is done on larger scale or in an academic laboratory where money is of an issue. And I would say personally for ourselves, this definitely is important, that we want to bring most of our syntheses back to catalog suppliers starting materials. But again, we can see here, you get the tool again, knows its chemistry, comes up with a route that is that we would be comfortable enough to run in the lab, robust, nice disconnection for the formation of the cyclopropanol here, and then late stage coupling to get to the final compound. Bringing us to the last molecule I want to talk to you about, which actually also I think will be the example that we'll talk about quickly later on, so I'll keep it brief for myself. This showcases sort of the workflow within the tool here. We can see that the last two disconnections here are really nice. The predicted route has this, it takes reductive amination to form the last ring here. And again, a sort of Michael addition to construct the one beforehand, leading us to the cyclic lactam as one of the starting materials. Now, this is potentially, as you can see in the bottom with the small shopping cart here, this by the tool is considered a commercial starting material. And actually, I also believe that it's actually commercial on Sigma Aldrich. Again, however, it's very, very, very expensive. So if I want to do this, I will not be able to afford this kind of starting material. Luckily now, we're able to trace back this molecule here by clicking the plus sign and tracing it back to starting materials that we are more comfortable working with. And we can see this here, just through two steps. These are known steps. They're just nicely integrated into the route. We trace it back to now starting materials that cost, I think, less than $1 per gram. So very, very inexpensive starting materials. And again, it just showcases, we have here a multitude of different reaction conditions. We can pick all of the published reactions are available to us here. You can see that we up here choose the reductive amination with ammonia at high pressure. This would be easy enough for us to run because our laboratories have very good high pressure facilities. However, for example, if somebody wouldn't have access to those, they easily could choose a different of the published routes towards this intermediate. With that, I hope that I sort of showed you a nice overview of the different capabilities of the predictive retrosynthesis tool and how we used it within our group to predict routes towards a variety of different natural products. But there's one thing, if we just show you routes on paper here, another thing is that we demonstrate how a search for a route goes in the tool directly. With that, I want to hand it to my colleague, who's not in the same building as me currently, but and he will give you a demonstration for how the tool performs live.